Okay, welcome back. We're going to finish this section about the isentropic efficiencies by looking at the isentropic efficiency of a nozzle. Okay, and like all the other ones, the important thing is not that much to memorize it, but to really understand it. What is the function of the nozzle? That way it's easy to define what would be the efficiency. So if we do the sketch of a nozzle, this is what we have. So let's say you have an inlet, and generally what you do on the nozzle is what? Is to accelerate a flow. So let's say you have the in-mass flow. This will be the same at the exit. And here generally you have a high pressure and high temperature. Those two go together. If you have a high pressure, generally it goes with a high temperature and a certain velocity. So what's going to happen to the nozzle? The pressure is going to decrease. So if the pressure decreases, then the temperature decreases. But obviously the goal is to accelerate the flow so that the velocity will be, this one should be lower than V2. Okay? And if we treat this problem as a normal control volume problem, this is over here our control volume. Alright, and if we do a figure, an HS diagram, will be in most cases in this area. So let's say this will be your P1, this will be your P2. So we'll be going from a high pressure 1, if it is, and if we assume it's isentropic, it will be here S1 equal S2. But you know that the actual case should take more energy, or you will waste some energy, so you have to move towards the right. So it will mean that the other case will be over here as 2. Okay? So here what you need to pay attention is that what is the difference between the height of these two. So I'm not going to put any value here yet. Okay, so obviously you see that this one is higher than this one. So the efficiency of the nozzle should be related to what? Should be the actual divided by whatever happens on the isentropic. So what type of energy are we dealing on the nozzle? Basically we're dealing with kinetic energy. So in a certain form what we could say is that the kinetic energy of the actual process will be divided by the kinetic energy due to the isentropic process. So this will be the general definition. So now you can write this as 1/2 m dot V2 squared, this will be the actual, divided by 1/2 m V2 isentropic square. So now, depending on the textbook you use, they have either one of these two expressions. But the important part here is really this one, to see what is the meaning. So this would be equal to what? Some books have this, but really you could eliminate the 2. Okay, personally, I like more this one. Alright, so this would be the efficiency of a nozzle. Okay, and now if we needed to look at this figure over here, so what is the difference over here? This will be V2 squared over 2, and this would be V2s squared, basically over 2. So from here you could say that actually you could say that H2S would be equal to what? H1 plus V2S squared over 2. Okay. But okay, the last thing we need to know about this is that, let's say you write down the first principle of thermodynamics for this control volume. So let me just do it very quick over here. So for this control volume over here, 1, 2, okay. So for the above control volume or open system, what do we have? Power plus m dot h1 plus 1/2 m dot v1 square. We neglect completely the potential energy. Let me put it here, but let's say we're going to neglect it. This should be equal to what? Oh, over here the m dot h2 plus 1/2 m dot v2 square plus m dot gz2. So as you can see in this nozzle, and that's generally the case, there is no heat gain or lost, and there is no power. So in most cases, what you have is what? And as well neglected the potential energy. Then you can cancel out all the different amps on both sides. You end up with the equation H1 plus V1 square over 2 will be equal to H2 plus V2 square over 2. Okay, so generally that's the equations you will have to deal with. So either you use nozzle, remember you have this figure, you might have this. This is the general expression for the efficiency, and if needed, you might have to deal with the expression of the control volume. Alright, so in the next video we'll do a quick example. So thank you for your attention.